Yo, what's up, folks? Here we are, the last unit, the last dance, the last something or other. So, modern physics. We call this modern physics, which means that it's really the last 100 years of physics. Um, this specifically, the first thing we start with, called I'll tell you in a minute, um, was one of the things that Einstein won a Nobel Prize for, I believe, in 1925. Um, but quantum mechanics, sorry, quantum physics, not really quantum mechanics, but quantum physics is and was a huge break from what we call classical physics. Classical physics means that you know exactly the answer to things, and quantum physics has to do with the idea that you don't necessarily know the answer to anything. That's a big, big difference. All right, so I can't tell you the history of this other than someone came across the fact that if you have a circuit that looks something like this, and we got this metal plate over here connected in a circuit, and there's this thing over here called a collecting plate with some space in between, maybe an evacuated space. You'd really literally put this thing in like what we call a vacuum chamber and suck all the air out of it. There's this variable power source. We'll get to that in a minute. But what you do is, or what happened was, people shined light on this metal plate. All right, and what happened is that current started to flow that we could read on this ammeter. All right, and what that means is that if current started flowing, it means that this metal plate must kick off or emit electrons. All right, shining light at metal makes the metal emit electrons, or it can at least. All right, and that's called, electron. That's called the photoelectric effect. All right, that's something you need to know. Oh gosh, what happened? There it is. All right, the photoelectric effect is, is that metal ejects electrons when it's hit by light. All right, now, not a huge surprise, hopefully, but you make the light brighter, and that made more current. Now, that could mean one of two things happens. One, it could mean that plain old, as the light gets, well, if there's more current, that could mean more electrons are ejected. Because if light is like a wave, and the wave gets, or the light gets brighter, that means the wave gains greater amplitude. Amplitude, of course. So it could mean that. Plain old, if light makes electrons come off, then brighter light makes more electrons come off. Fair enough, could mean that. It could also mean this, that it's not more electrons, but it's that electrons with more energy come off when the light gets brighter. All right, so which one is it? And here's what I have come to understand in the last few years. This is really, really tricky for kids. Not that it's easy for adults, because I'm having a hard time with it myself right now, because I haven't looked at this in a while. But, the deal is, if we treat light like a wave, like we have so far in everything we've done, right? Optic stuff, ray diagramming, diffraction, interference, light behaves like a wave. It does. All right, so if light is a wave, then which one of these is the better explanation for a brighter light making more current? Well, the answer is that if light's like a wave and energy is controlled by amplitude, well, then it should be that number 2 is true. If we send more energy in there, we ought to get electrons with more energy to come out. So the answer is, wave theory says that number 2 is the right explanation. Make sense so far? Right? Both of these could be possible explanations for why there's more current. It makes sense if light behaves like a wave, that if the light is brighter, the wave has more energy, Therefore, the electrons should have more energy if energy is conserved, right? Make sense? Okay. Yeah, amplitude. But here's where it gets wacky. All right, here's what you can do. You take this, what do you call it here? We're kicking electrons off into this, into this. Those are negatives going this way. Electrons come off there, right? We get some reading in our ammeter, right? But what we do is we turn this variable. That's what this means, variable. So this is a variable power supply. It's a knob, right? We turn the knob to make this end more negative over here. And what that does, if this end is negative and electrons are trying to get over here, well, this negative repels these electrons. And we turn that potential up to a certain amount, and we stop the current altogether. Or we apply what's called a stopping voltage, or sometimes you call it a stopping potential. I'll just write potential. All right, so with this power supply turned to 0, or just turned off, we get current to flow. Current flows, current flows, current flows. All right, we turn this, knob from 0 up to something, and suddenly we get, at just the right level, we get current to slow down all the way to 0. All right, that's when we've reached our stopping potential. Now, here's what gets weird. All right, we stop the voltage, we stop the current, and then we make the light brighter, but still current will not flow. No matter how bright you make the light, current will not flow. All right, now let's think about what we said on this last slide. Light behaves like a wave, right? The brighter the light is, the more energy there should be. So here, what we're saying is we've gotten to a certain energy per charge, voltage, such that these things don't have enough energy to get across. So why don't we just add more energy, right? Let's make the light brighter and have more energetic light. But that didn't work. So this totally disagrees with wave theory and shows that the amplitude, or brightness, I'll say, or intensity of a light, I'm going to get rid of this word. Brightness of light does not always control how much energy it has. If it did, we could just make the light brighter, give those electrons more energy, and have current run again. Okay? Yeah, forget about that. However, what you can do is change the color of the light. And more specifically, change it towards the violet end of the spectrum. And that would make current start flowing again. And that would require an even greater stopping potential to make the current stop. Changing the color of the light. So what this says is that light sometimes works where energy is related to color, or, does it pop in here by itself? Frequency. Total separation from wave theory. All right, that's tricky stuff, real tricky stuff. All right, what we're using, I know I'm taking a long time to get through this, and I'm saying it over and over, but what we said before, if light behaves like a wave, no matter what, brighter light, more energy. Good. Got some Black 1 peeps in here. Good Black 1 action. Good kids. Good people. So where are we at? Yeah, I think we were saying, tricky, right? So light, typically, we treat it like a wave. The light gets brighter, that means more energy, right? Which means that if we shine brighter light at our metal plate, why wouldn't that pick off electrons with more energy? Well, apparently it doesn't, because this is a control really of energy per unit charge, the voltage. Right? We set that to a certain setting that doesn't allow these guys to keep jumping across. no matter how bright the light gets, they still don't jump across. So brighter light does not give those electrons more energy. What does give them more energy is to change the color of the light. So light, sometimes we can relate energy to the frequency of the light. And what this shows, I mean, basically this says that, okay, well, light doesn't behave like a wave all the time. It certainly does sometimes, but it doesn't always. Sometimes light acts like little bundles or packets called quanta, singular units of energy that we call photons. Photo is like light. On part is like particle, electrons, neutrons, protons. Photons. A photon is a particle of light. Where we say the photon's energy is proportional to frequency. In a simple equation we call E equals hf. E is photon energy. F is photon frequency. And H is called Planck's constant. And there, oops, hang on. And there is there is the value of Planck's constant. Notice, hopefully, of course, this can be measured in joules. Uh-oh, that can be measured in hertz. Those are hertz. So Planck's constant is in joule seconds. So this is right, HF, joule seconds times frequency, hertz. Well, that's joule seconds times 1/seconds. That's what a hertz is. Oh yeah, we end up with energy in joules. Okay? Fair enough? All right, so let's use this to solve a couple of straightforward problems. What's the energy of a photon whose frequency is 620 terahertz? Or how about 310 gigahertz? Or how about 46 megahertz? 3.10 gigahertz, excuse me. Determine the corresponding wavelengths and state the classification. Oh my goodness. Oh, pooh, you're going to need something else. But we'll bag that part. We'll get to it on Monday. So, let's see. Energy of a photon whose frequency is. So, well, we're just going E equals HF, 6.63 times 10 to the negative 34 joules seconds times 620 tera times 10 to the 12th, I believe, hertz. Confirm that? Yep. So that one is, let's see, 6.63 E negative 34 times 620 E 12 equals 4.11 times 10 to the negative 19th. And then the 3.10 gigahertz. So 6.63 E negative 34 times 3.1 giga means 10 to the 9th. So that's E is 2.05. Well, we'll call it 2.06. 10 to the negative 24th. And the third one, 46 megahertz. 46 mega 10 to the 6th. 3.05 times 10 to the negative 26th joules. All right, so there's part A. Whoa, except it says calculate the energy in electron volts of those photons. So what the heck fires an electron volt? Well, apparently it's an amount of energy, right? If we're calculating energy in electron volts, then electron volt is a unit of energy. And it's literally the amount of energy that an electron gains, the amount of kinetic energy it gains, if it's allowed to accelerate through a potential difference of 1 volt. All right? Now, 1 volt, by definition, is an amount of work or energy per unit charge, right? So that amount of energy is equal to Q times V. Well, what's the Q? The Q is the charge of an electron, and the V is 1 volt. So there is an amount of energy that's equal to an electron volt. That's just um, a conversion factor. By definition, that's what an electron volt is. It's like saying, what's a foot? A foot is 12 inches. What's an electron volt? An electron volt is 1.6 times 10 to the negative 19th joules. Okay? So, over here, we would say, let's see, 1.6 times 10 to the negative 19th joules in 1 EV. And then we go, let's see, 1, 6. So this is 2.57. And then this one, 2.06 E negative 24 divided by 1.6 E negative 19. 1.29. It's a 9. EV. And this one, 3.05 E negative 26 divided by 1.6 E negative 19 equals 1.91 times 10 to the negative 7th. Fair enough? Now the corresponding wavelengths, well, remember, photons are still light, all right? And light still travels at the speed of light. So we can still relate frequency and wavelength with C equals F lambda. Really, V equals F lambda, but this is the speed of light. All right, so wavelength is C over F, where C is 3 times 10 to the 8th. Our frequency here is 620 times 10 to the 12th. 8, 620, E12. Well, this is actually 484 nanometers, or 4.84 times 10 to the negative 7th meters. Trust me, those are the same. 3E8 divided by 3.1E9. Yeah, so this is actually, well, 9.68 centimeters. And then last one, 3E8 divided by 46E6. This is 6.52 plain old meters. Okay? Monday we'll talk about this part, the classification of each on the electromagnetic spectrum. We'll talk about that. Okay? But a good little start on what photons are and how we saw evidence for them, or how we saw evidence that light can behave not like a wave, but behave like a particle, or a little packet bundle of energy. Okay, my friends? I hope you had an enjoyable break. Hope you're well rested for the final push. We're going to crush that AP exam, my friends. Crush it. May 13th, high noon. You know what that's from? It's from a John Wayne movie. Okay, so we will see you soon, guys. Bye. Bye.